The Large Hadron Collider is widely regarded as one of humanity's greatest scientific achievements. The 17-kilometer-long accelerator smashes particles together at high speeds and looks at the products to search for new physics. So far, we've learned a ton about the smallest things in nature, such as quarks, which are tiny particles that make up the atoms that compose people, planets, stars, and everything else we can see. A few years ago, physicists discovered strange new particles known as pentaquarks. We knew they were made up of 5 quarks bound together, but their properties and structure were a mystery. Now, brand new results from the LHC provide significant insight into the nature of these puzzling particles. Thomas Squarnici from Syracuse University in New York told me, Ben McAllister, all about it, starting with the initial discovery of pentaquarks.
Everybody was kind of depressed. Some people even put in writing that maybe pentaquarks don't even exist. But we found a signal in our data that just was very strong and could not be explained by anything else but by being a collection of 5 quarks. The amount of data that we had 3 years ago was not overwhelming, so we got rather fuzzy picture. Since then, our experiment, the Large Hadron Collider, kept colliding beams, and we managed to accumulate much larger data set, and this gave us much crisper view of what we were seeing.
So at the previous study, you guys were able to confirm that these pentaquarks existed, but you didn't have a very clear picture of what they looked like. And the new data has enabled us to get a much clearer picture of what's going on sort of inside a pentaquark. Would you say that's fair?
This is very fair. After our first paper, there were a lot of theoretical papers published which proposed different models of pentaquarks, and they often differed a lot in terms of what kind of substructure such complicated systems would have.
What were the sort of main competing models?
2 main models were so-called tightly bound and loosely bound pentaquark. In tightly bound system, you have 5 quarks that kind of interact directly with each other. And if these quarks see each other directly, they will clump together tightly. So we say it's a tightly bound or compact pentaquark. And the other model says you will have a subdivision into 2 parts, one with 3 quarks and the other part quark antiquark.
So these are the 2 models then, right? There's the one where you've got these 5 quarks that are sort of tightly bound directly to each other, and then the model where you've got a group of 3 and a group of 2, and then those 2 little subgroups are bound to each other more weakly than in the other model?
So they don't feel strong attraction to each other, but if you get them close enough, they might start feeling a little bit of attraction. And this is again very similar to what is happening with atoms. If you get them close to each other, they start feeling a little bit of electric force, and this is exactly what is responsive for creation of molecules. That's also the reason why we often call the second class of models molecular models.
And so what did the new study at the LHC be that we're talking about today? Which of the 2 competing models did it point to?
It became clear that data favored this molecular model. There are 2 indications in the data for that. We see 3 narrow states. Narrow means that mass is well defined. And when mass is well defined, it means that the particle is more stable. So there's some mechanism which gives them rather good stability. And that molecular model provides such mechanism.
Okay, so the fact that the pentaquarks, they're sort of more stable, they last a longer time, points strongly towards the molecular model.
I should mention that there is a second feature of new data. We discovered a new peak in the data, a new pentaquark particle, but with the mass which is different than what we were seeing before, but of the same family. The mass of this new pentaquark points in the same direction of this molecular model. So that's also a very strong indication.
So we have quite a lot of indication that the molecular model, as opposed to the tightly bound model, is correct for the pentaquark substructure. What are some of the other areas that our deeper knowledge of these quarks and their interactions might impact?
From this new observation, we can anticipate better what kind of new particles we can look for in the data. These observations don't have immediate impact on our everyday life, though you never know where some discoveries today might impact the technologies of the future. However, there are places in universe where matter is in a very different form, and one of these places are neutron stars.
Right, they're like a combination of neutrons altogether the size of one star, like one giant atom, right? These weird exotic structures out in space.
Right, but these are clumps of quarks, so this could change astrophysical models of these objects.
Some fascinating new insights that help us better understand the universe from the very small scale of particle interactions, potentially all the way up to the very large scale of astronomy. That paper will be submitted shortly to Physical Review Letters.